Hubble has been orbiting Earth for over 34 years, and during that time, its mission has been nothing short of extraordinary. Originally designed to explore the vast universe beyond our solar system, it was not specifically built to study nearby celestial objects. Despite this, the Hubble Space Telescope has managed to observe many intriguing features within our own solar system, providing unique insights into planets, moons, asteroids, and even rare cosmic events. These observations have allowed scientists to gather data that would have otherwise gone unnoticed, filling gaps in our understanding of our cosmic neighborhood. What makes Hubble's achievements even more remarkable is the fact that not every planet or object in our solar system has a dedicated spacecraft mission. While missions like Voyager, Cassini, and Juno have delivered incredible data about specific planets, Hubble has served as a flexible observer, capturing images and phenomena across the solar system. Its versatility and long lifespan have allowed it to document events that are transient and difficult to predict. More than just focusing on planets, Hubble has looked at moons, comets, asteroids, and atmospheric phenomena, revealing the complexity and richness of the solar system beyond what was initially expected from its mission. Our journey through the solar system with Hubble begins close to home, with the Moon. Because of its proximity and large apparent size in our sky, Hubble cannot photograph the entire lunar surface in a single frame. This limitation, combined with the fact that other missions like NASA's Lunar Reconnaissance Orbiter provide high-resolution, detailed maps of the Moon, has made lunar imaging a lower priority for Hubble. Its observation time is generally reserved for more distant or less accessible targets. However, this does not mean the Moon has been completely ignored. In 2012, during a rare astronomical event known as a transit of Venus, Hubble was used to observe the Moon in a completely different way. Instead of photographing its surface, scientists treated the Moon as a massive mirror. As sunlight passed through the atmosphere of Venus and then reflected off the Moon, Hubble captured the subtle changes in light. These variations were used to analyze Venus's atmospheric composition. Although Venus's atmosphere has been studied extensively in the past, this experiment served a different purpose. It tested whether the method of using light scattering to analyze distant atmospheres was reliable. This technique, when perfected, becomes an invaluable tool in exoplanet research. By observing the light from distant stars as planets pass in front of them, Hubble can detect how the starlight changes due to the planet's atmosphere. Since the Sun is far too bright for Hubble to observe directly, using the Moon as a reflective surface was an ingenious way to test the effectiveness of this method. The experiment confirmed that this approach can provide accurate data, boosting confidence in similar techniques applied to far-off exoplanets many light-years away. While the Moon poses some observational limitations, Hubble has had far more success observing Mars. Unlike the Moon, Mars can be captured in its entirety in a single image due to its smaller apparent size and greater distance. Hubble has provided countless global views of Mars, which are especially useful during times when Mars is in opposition, when the planet is closest to Earth and fully illuminated by the Sun. These images are not only visually stunning, but also scientifically valuable, revealing details about the Martian atmosphere, dust storms, and surface changes. One of the key contributions from Hubble's observations of Mars is the monitoring of global dust storms. These storms can last for weeks or even months and can obscure the planet's entire surface. Hubble has documented such storms in time-lapse sequences, giving scientists insights into their evolution and impact. This information is essential for planning missions to Mars, especially those involving rovers and landers, as dust can interfere with solar panels and visibility. By understanding the seasonal and environmental changes on Mars, researchers can better prepare for future human exploration. Hubble has also captured the motion of Mars's two small moons, Phobos and Deimos. These tiny moons orbit the planet rapidly, with Phobos completing an orbit in just 7.5 hours, making it the only known moon in the solar system to orbit faster than its host planet's rotation. Hubble's time-lapse imagery shows Phobos racing across the Martian sky, offering not just a dramatic visual, but also data on its trajectory and orbital behavior. In one instance, Phobos was observed over just 22 minutes, with its swift motion providing valuable information about its gravitational relationship with Mars and its likely future, which may involve either crashing into the planet or breaking apart into a ring system. As we move past the inner rocky planets and head toward the outer solar system, we first encounter the asteroid belt, a region teeming with countless rocky bodies of all shapes and sizes. Among these is a peculiar object called asteroid 6478 Gault. First imaged by Hubble in 2019, Gault immediately drew attention because it displayed two long, thin tails, traits normally associated with comets. Yet, this object resides squarely within the asteroid belt and is officially classified as an asteroid. The mystery of Gault's comet-like behavior lies in a phenomenon known as the Yarkovsky-O'Keefe, Radzievsky-Paddock (YRP) effect. Solar radiation, though weak, can exert pressure on irregularly shaped bodies. Over time, this can cause them to spin faster. In Gault's case, the 3.5-kilometer-wide body has been accelerating in its rotation, now completing a full spin in just 2 hours. This rate is right at the threshold of structural integrity for such bodies. As a result, centrifugal forces exceed the weak gravitational cohesion holding the asteroid together, flinging loose material off its surface and forming the twin tails seen in Hubble's images. This behavior reveals something profound about asteroids like Gault. Rather than being solid monoliths, many of them are actually fragile rubble piles, collections of boulders, pebbles, and dust loosely held together by gravity. As these bodies are disturbed by radiation, collisions, or gravitational interactions, they can begin to shed material or even disintegrate completely. Gault's activity is likely a prelude to its eventual demise, making it a perfect subject for scientists studying the life cycle of small bodies in the solar system. Another compelling example from the asteroid belt is P/2010A2. Initially thought to be a comet due to its tail-like structure, it was later determined to be the product of a collision between two asteroids. Hubble's high-resolution imaging revealed a unique, X-shaped pattern near the nucleus, a configuration created by the high-speed impact. Such collisions are extremely rare, as most objects in the asteroid belt follow stable orbits. Still, when two bodies do collide, the results can be both visually dramatic and scientifically valuable. The P/2010A2 collision produced a cloud of debris consisting of dust, rock fragments, and ejected material moving in various directions. This debris does not spread out randomly. Instead, it follows paths dictated by the momentum and gravity involved in the collision. Some fragments fall back to the surface of the remaining body, while others escape entirely, drifting off into space and forming tail-like structures. These are not icy tails like those of a comet, but rather dusty remnants of violent, high-energy impacts. Observing such events allows scientists to better understand how asteroids break apart, how rubble piles form, and how the solar system evolves over time. While the asteroid belt is chaotic, it is not without order. Most of its residents follow relatively stable paths around the Sun. However, when an object strays from this zone, either due to gravitational interactions or other disturbances, it may encounter Jupiter, the largest planet in our solar system and a massive gravitational influence. Sometimes referred to as the solar system's vacuum cleaner, Jupiter's immense mass exerts a powerful pull on passing objects, often diverting or capturing them. A historic example of Jupiter's gravitational power occurred in 1994 when comet Shoemaker-Levy 9 collided with the planet. Originally a single 2-kilometer-wide comet, it had been captured by Jupiter's gravity years earlier. As it passed too close to the gas giant, tidal forces tore it apart into multiple fragments. These fragments continued orbiting Jupiter for a while before finally plummeting into its atmosphere. Hubble was among the telescopes that captured the momentous event, making it the first time humans directly observed an extraterrestrial collision. The impacts were spectacular. Each fragment struck Jupiter at speeds of around 60 kilometers per second, more than 210,000 kilometers per hour. The result was a series of explosions that generated towering fireballs and dark impact scars. One of the impact sites measured about 12,000 kilometers in diameter, approximately the size of Earth. The energy released by the most powerful strike was equivalent to 6 million megatons of TNT, a force more than 600 times greater than the world's entire nuclear arsenal combined. Hubble's documentation of the Shoemaker-Levy 9 event not only showcased the telescope's observational power, but also reinforced the idea that Jupiter serves a protective role in our solar system. By capturing or deflecting comets and asteroids that could otherwise threaten the inner planets, Jupiter reduces the risk of catastrophic impacts on Earth and its neighbors. Other, smaller impacts have since been observed on Jupiter, each contributing to our understanding of how giant planets interact with smaller bodies in space. Hubble's unexpected and extended journey through our solar system has provided insights far beyond what was originally envisioned for its mission. From reflecting light off the moon to test methods for exoplanet studies, to observing dust storms on Mars, to documenting the destruction of comets and the evolution of asteroids, Hubble has proven itself as more than a deep space telescope. It is a versatile, tireless observer that continues to unlock secrets not just from distant galaxies, but also from the dynamic and ever-changing solar system we call home. As long as Hubble remains operational, its keen eye will continue to reveal the extraordinary hidden stories unfolding in the space just beyond our reach.